Ladies and gentlemen, I'm Bonnie. On behalf of Social Enterprise Research Academy, I would like to extend my very warm welcome to all of you. We are very privileged to have the golden opportunity of hosting the second Nobel Laureate Public Charity Seminar for the youth in Hong Kong, to have a chance to meet Nobel laureates and participate in their conversations as audiences, which inspire us to see things in life from a new dimension. We hope all of you will enjoy the program that we line up for you.
Right, okay. Good evening, class. Come on, students, where's your energy? Okay, sorry, 我哋唔好搞到咁悶。大會要求我用英文，咁啦我就轉返英文。Okay, because it's in English, so I'll speak in English, okay? So, well, the rundown is there, it's very clear. So I just wanted to start with two quick questions, okay, for the students. Now, how many of you sitting here, you study science subjects? Wow. Okay, now, those of you who raise your hand and you study science, be honest to yourself. How many of you would like to become a scientist in future? Wow, please take a look like that. Oh, come on, the others, don't be shy. Okay, I'm asking if you want to. All right, you should not stop dreaming about your future. Well, we have a very interesting, talented individual, okay? And we will like to hear from him. And so I'd like to invite him to the stage because I don't want to get into these very formal, boring, long introduction. So please give a big round of applause to Aaron Liu, a Ph.D. student from MIT. So Aaron, please have a seat.
Thank you.
Okay, so how are you, Aaron?
Hey, I'm good. How are you?
I'm good. Okay, so a little, let's get closer.
All right.
Okay. Okay, so, well, I'm sure they have, the students like to read, and I'm sure they have read the book, they know more about from there, but let's get a little lively.
Yep, sure.
Otherwise, the students will start falling asleep like in lessons.
Class, right? Yep.
Yeah.
Exactly.
We do a lot when we were students. Okay, now, so Aaron, we knew that you were actually an old boy from DBS. Any DBS here? I see DGS there. Anyone from DBS? No. Okay. So, but DGS is here.
Yeah.
Okay. And you also studied in LPC, Leopoldchen United World College. Yeah. So tell us something about your secondary schooling. How was it like?
Well, DBS and LPC are very different. I'd say they're the polar opposites. I'll tell you what it means, right?
Okay.
In DBS, we're raised under a culture where people think we got to be the best of the best.
I think that's a fact, isn't it?
Well, people try to make students best of the best, right? Everybody says we're the best of the best, right? I do not think I am, but a lot of students do think that way. So the reason for that is because they want us to focus on one thing or something to be really good at it. Either music, either sports, either academics and stuff like that, right? So a lot of times students would be uncomfortable stepping out of their comfort zone because they're so, in order to be good at what they do, it requires a lot of dedication. So maybe like students practice sports 8 hours a day outside of school. So they don't really have much time for anything else, right? LPC is very different. LPC encourages students to fail, to do things outside of their comfort zone. And that's the polar opposite of DBS. So when I was at LPC, I tried a lot of things like lion dance, dragon dance, lighting crew in charge of like the stage lighting and stuff like that. So I was able to perform really poorly or mediocre, right? Like, and people still accept us for who we are. So it gives us the courage to try different things. So I'd say two schools are very different, but both are very important.
So let me take you back a little bit. Like you just mentioned, you have to do 8 hours, like in DBS, you have to do something that you are good at.
Right.
So assuming, no, actually you are one of the best. So what was the thing that you were very interested and that you spent 8 hours, 10 hours, 20 hours in DBS?
So I played the violin back then. So outside of DBS, I was a student. I was a junior student at Hong Kong Academy for Performing Arts. And I played in the Junior Symphony Orchestra there, and I was in the Junior Chamber Orchestra as well, along with the 2 orchestras at DBS. So that took up quite a part of my life.
So you mentioned something about your interest in arts, in music, and being in the seminar here. Yeah. So let's talk about science. So what about your science?
Science.
So how was your science when you were in DBS or in secondary school?
It's quite a story. So like a lot of local schools, we had to pick a track, right? Either science or arts track. And when I was at DBS, I didn't get to experience what physics, chemistry, and biology until I was in Form 3, because I studied under the local education system. And that was a time where I was like, oh, wow, I'm good at science, and I really enjoy it. But because of my obligations in music, I didn't really get to explore science to the fullest, because I had to compete, I had to train, I had to do a lot of different things in arts.
So what you have just mentioned, like in DBS, you were struggling with your time, your passion was in music, but you also like science, but the music was pulling you apart. And then when you went to LPC, fixing the lights day and night there, and doing this lion dance, dragon dance, and tiger dance, if there is any of them. Yeah. So then you finished your secondary schooling. Yep. So you tell us about your university life.
Sure.
So because what I know, the LPC graduate, very dynamic.
Right.
And they end up in some good places. So where did you end up?
I ended up at Brown University, which is a school in the U.S. It's in Rhode Island. And it's a really awesome school. I think it's a very special place. And it really helped me develop into a person, who I am today.
So what was your major?
I majored in biochemistry and molecular bio. So for people who don't know what biochemistry and molecular bio is, we study the interaction of protein-protein interactions within the body. So I wasn't clear until I was a sophomore, so thought I cleared that up here.
Okay, so what job did you end up? Did you end up in a lab after study this what did you say, sorry?
Biochemistry, yes.
Biochemistry.
Yes. Yeah.
So where did you end up?
It's a funny story. So I did 2 years of biochemistry research when I was an undergrad, and I realized that I didn't really like it as much. So I switched over to doing organic chemistry research for my last 2 years of college. We had 4 years of school. And then afterwards, I realized that, hey, as a scientist, I've got to pick a job that actually fulfills my duty as a child in Hong Kong, like family values and stuff like that, where we gotta really make money and stuff. So I decided to go for a job on Wall Street. Applied to investment bank jobs, and then ultimately got a job in investment banking as a sales and trading, as a trader. And then I moved over to hedge funds, and I spent 2 years as an analyst, and then I got promoted to portfolio manager in 2015. And I was managing our fund's healthcare and special situations portfolio, and I've been doing that for quite a while.
So, you need to explain one thing.
Okay.
Like in Chinese, there's a saying, like I always hear in TV as well, like 你嫌錢腥啊?
Okay.
Like what was the money smell? If I translate it to English. Like, this gentleman was, I'm sure, like, if you're working on Wall Street with the bonuses you have, like, you're making big amount of money. And did you hate the money that much, so you quit the job? Like, what changed your mind?
Right. So I guess the inflection point was that I moved back to Hong Kong in mid-2016. And during that time, I spent 6 months reconnecting with a lot of my friends in high school, middle school, and branched out. Got to know a lot of new friends. through my existing connections. And we had a lot of dinners. A lot of these friends work in finance. They're doctors and lawyers. So a lot of our dinner conversations, the same question always comes up, right? How do we make more money? That's literally the question that comes up all the time in all of our dinner conversations. That really prompted me to think about, do I really want to make finance my career? In other words, do I really want to make making money the top priority in my life? And my answer was no, because I wanted to do more. So I went back to the drawing board and thought about what I'm really passionate about, what I really like. And I realized I like the scientific and R&D aspect of my job a lot more than the investment decisions that I had to make. So that's why I decided to go back to science. Now, that's the first question. The second question is, what's science, right? Now, I really enjoy reading translational chemistry papers and organic chemistry papers and reading the synthetic pathways within patent filings and stuff like that. So that's why I wanted to go back to chemistry. Now, after I figured out I wanted to do science, I wanted to do chemistry, the third question is, what subfield of chemistry I want to be doing? So fortunately, I really enjoy initiating projects. I really enjoy answering or coming up with potential solutions to unanswered questions. I really enjoy independent research. I really enjoy teaching. So I realized that all these things kind of point towards the fact that I want to be a professor, ultimately. Right. So I wanted to go back to school, to grad school, to acquire the skills under an apprenticeship, under a certain professor, learn most, if not all, the essential skills for me to succeed as an independent researcher. So that's why I decided to go back to school.
So you're going to do your Ph.D.?
In organic chemistry.
Okay,
yes.
So guys, Ph.D. doesn't stand for Pizza Hut delivery. It stands for Doctor of Philosophy. So in MIT. So what are you, like, I'm sure you'll be spending another 4 to 5 years.
Yep.
So can you briefly, don't get into details.
Right.
Very briefly, tell us what's your proposed research area will be.
Sure, sure. Before we start, I just want to do a quick poll because I wanted to see how many of you think that within my 5 years of PhD, I'd be studying for 5 years. Nobody thinks that? Okay. So do you guys think that I'll be working for 5 years? Okay, nobody thinks that. Okay, so...
I think...
Okay, maybe they should raise their hands.
No, actually, you guys should just raise your hand.
Okay.
Not smart.
Okay.
Yeah, okay.
Let's do it again. Sorry, I wasn't clear.
No, actually, like what you wanted to ask was whether that 5 years, is it really studying?
Right.
Is it going into the classroom and learn, or was it more than something else?
Right. So I'd be doing research for 5 years, and like you asked, like what kind of research that I'd be doing. I'm thinking more towards, well, like right now I'm going to be working on carbohydrate chemistry. So for those who doesn't really understand what carbohydrate chemistry is, carbohydrates are essentially sugar molecules. So I'm trying to figure out how to functionalize these sugar molecules. Functionalize meaning introducing certain functional groups into these molecules to allow them to perform certain actions in a human body or as a drug, right? Because the reason why a lot of these pharmaceutical companies couldn't make a really diversified portfolio of, or library of drugs is because they might be limited by the methodologies out there, right? So we're using the same methodologies over and over again. And I'm more interested in developing new methodologies to enable medicinal chemists to create new molecules as a drug candidate instead of myself developing a drug candidate.
Well, Aaron, I can see from your passion, you have actually made a very wrong decision. After graduating from university and work in Wall Street, you should be in a science park or all these different parks and work in those labs. But anyway, there's never late if you materialize your dream. As teachers, we always encourage our students, why not? So, like you being one of the victims who didn't have a good, well, I don't know, I wouldn't say a good planning, but didn't really see the whole picture and surrender yourself to the values that I need to be a money machine so that my boss, like your parents, are happy with you. So you make them happy, and then after 2 years, you go back to study. So there are young individuals here, like these kids. So what do you think, like from their perspective, like if they want to study science like you, what top tips? Well, anyway, let me just sell I have a YouTube channel. It's called Top Tips with Something. So don't let me promote that YouTube channel. If you find it out, remember to subscribe, like, and share. But anyway, go back to this. Sorry, that was intentional.
Yep.
Okay. So, do you have any top tips for the kids if they want to pursue science and get into the science field?
I see. I'd say top tips is, well, pretty cliche, but follow your heart, right? Like, no matter what you do, don't let others tell you what you can or can't do, because a lot of times they don't understand where you're coming from or what you're really interested in. Because a lot of times, I think especially here in Hong Kong, it's really hard for us to pursue something that we really like. I see the problem of twofold. Like, the first problem is a lot of times we're under the stereotype where smart students or star students have to study medicine, have to study law, have to study or go into finance, right? Because that's where most money is being made, or there's a certain prestige associated with that. It's hard to not succumb to this, because I myself, succumb to this stereotype as well. The second problem is, even if you do pursue science, right, it's hard to convince your parents afterwards to get it, to stay in a job in science that doesn't pay as well as other jobs here in Hong Kong, because ultimately we also need to fulfill our duties as, it's like children,
a good
sons
son.
and daughters, right? Yeah, exactly. So we gotta, contribute to a certain extent, and it's pretty hard to do that with a job that doesn't pay as well. But I'd say, if science is your passion, you got to go for it. There are lots of opportunities out there where you can go to schools in the U.S. where it's completely need blind, where it's merit-based scholarships, where if you demonstrate a certain level of aptitude, they would give you the money to go study. And then for PhD programs, it's the same. Like, they would pay for you to go there and pay for your living expenses and stuff like that. So don't let anything stop you, right? Like, go look for opportunities, and there are a lot of fellowships where you can apply to get funding for you to pursue a career in science.
So let me recap the top tips. So Aaron's top tips, number 1, you can write down your note. Follow your heart. And top tips 2, turn your passion into profession. And that was Aaron. Please give him a big round of applause.
Thank you.
So, I hope the sharing just now would at least enlighten you to continue what you dream for if you are a science individual. So, let us move on. So, I guess the weather was very good today, and I don't think you want to know what is it tomorrow, even though we have the weather boss here today to tell us more, but not about the weather of today and tomorrow, and not about the forecast as well. So actually, Mr. Shun Chi-ming, the director of Hong Kong Observatory, is going to share with us, like as Aaron mentioned, some of the difficulties in getting some careers in science. It is exactly the topic of Mr. Shun, who will tell us science as a career. Ladies and gentlemen, so please give a big round of applause to Mr. Shun.
So first of all, I'm really pleased that we got so many students to come and join us. Of course, I also very privileged to talk to you and with Professor Kajita here. And definitely also my appreciation to the Social Enterprise Research Academy for inviting me here. So in the next 15 minutes or so, I'd like to share with you today why I choose science and physics as a career. Of course, today's topic about the mystery of the universe, I will leave the difficult part to Professor Kajita. But in fact, our path actually almost crossed, because when I was a young kid like you, all sitting around us here, I had a dream to understand the universe, especially the Big Bang. At that time, we were taught that the neutrino has no mass, but definitely this is now proven wrong by Professor here. So I'm not going to talk about that here, but I think also echo what Aaron has just mentioned. We need to have our dream and our passion first. Now, of course, another of my dream was to understand elementary particles, of course, including the particles that Professor has studied. And of course, our paths also coincide in the atmosphere, because Professor studied the neutrinos in the atmosphere, that I also get to study and actually do the forecast every day. So it was me, some more than 30 years ago, graduating from the University of Hong Kong physics. So at that time, I had to make a choice, really a difficult choice. First, my dream was actually inspired by many great scientists, like Professor Gauman, who was a pioneer in the elementary particle physics. He managed to inspire me because it's so simple, explaining the elementary particles in just really simple geometry, or we call group theory. It's almost like our book of change, I Ching, in the Chinese philosophy. And also very simple theory by another great scientist, Professor Feynman. I think some of you who has an interest in physics will know this name. Again, in those days, without internet, without Facebook, now we know that a picture is more important than the equations. So Professor Feynman actually came up with very simple diagrams to explain so difficult subjects. So, recently I came across his paper about what science really means to us. First of all, I think we need to appreciate the passion. Why scientists has a passion? In fact, it is the pursuit of the truth. And then you derive your happiness from solving the most difficult problem in the world. So I must imagine that when Professor got the results of the neutrino having mass, I think that's really a big excitement and enjoyment. And I think this inspires us forever to get to study science. Of course, science can also produce something new, or today we call innovation. But that something could be good or could be bad. If you think about the nuclear bomb, maybe it's not that good at all, or is a necessary evil. But science can derive many goods to the society, as I will explain, at least from my perspective. And of course, science, we never know that, even when we have Newton, we think that Newton is correct, and then we have Einstein. So nothing is certain. In fact, as a forecaster of the weather, I face every day the question of uncertainties and the difficulties in conveying the message to everyone sitting here. Now, very similar to Aaron, I got actually the opportunity to enter into MIT or Caltech when I graduated from school. But I decided not to because I was the only son of my parents. So I think I shouldn't go abroad to study, but instead I get into the Observatory Hong Kong. But why? I have the inspiration of doing science, doing physics, and also trying to get into the studying the universe, cosmology, galaxies. But maybe we find the same truth in typhoons. So yeah, this is also, yeah, I think there are many problems. No matter where we look towards in science, we still don't understand fully how the typhoon developed and intensified, even today. And so this is where I end up, and still, I'm still there after 30-odd years. But I think one of the very strong consideration is that I am able to learn, to continue to learn something new every day. So I think this is very important. And at that time, when I joined the observatory, my conviction was that if I could learn new things from the work, I would stay. Otherwise, I will go abroad and study. But here I am. I'm still learning every day, so I'm fully satisfied with what I choose. Of course, from day one, I have to forecast the weather. And last year, I have to handle my second number 10, the highest typhoon signal in Hong Kong. And I think all of you would remember that we were very lucky to escape from the full thrust of the typhoon, but Macau was not that lucky. We have 10 people killed by the storm surge. So, and this is what I also look at why in Macau it was so devastating, because you see the two gentlemen pointing is the level of the sea at the time. So you can see that why people got killed because of the flooding, the storm surge in Macau. And one thing that I think is really satisfying for me is that we have been doing a good job in managing the casualties from typhoons in Hong Kong. You can see that in the past, we had hundreds of people killed, even in the 1960s, 1970s, but nowadays, it's not just the result of the observatory's forecast, but also the modernization of the infrastructures. But our forecasts, our warnings play a role. And I think this is also the meaning from our work. And by the way, I have told Bonnie just earlier that we even had more serious casualties in the past due to typhoons. Have you heard that we had more than 10,000 people killed in Hong Kong because of typhoons? If you don't know, then you better pay attention. So this is the meaning that I think I could derive from my career in science. So we can do something good to the society. And I think many people joining the observatory has this commitment that we want to do something good for the society based on science. And also, after I joined the observatory, I also get into the project for the new airport at the time, 1997. If you remember, we built the airport at Chetlapcock. And I think it was quite well known for wind shear problem. So I managed a project to introduce the best system in Hong Kong to detect the microburst. By the way, microburst was also, I think, discovered by another Japanese professor, Professor Fujita, who studied in great details about aircraft accidents, why the aircraft was brought down by the wind shear. And then the scientists came up with the weather radar to detect it. So saving lives again. But it's not enough for Hong Kong. In Hong Kong, the wind shear didn't come from the microbursts, the thunderstorms, but it came from the mountains to the south of the airport, the Lantau Island, the terrain, which caused the wind shear. So the weather radar didn't work, and I have to introduce a new system known as the laser radar, the LiDAR system for Hong Kong. It hasn't been applied to detect wind shear around the world. So we were the first to develop this system, this technology, and make it work in Hong Kong. So we got reported around the world, including in the US Aerospace magazine. We got reported in the International Civil Aviation Organization about our work, that this technology was proven in Hong Kong. So I really enjoy the result of several years of innovation and teamwork with my colleagues. And we actually also won the award of the year from the ICT award. Of course, this is not comparable to the Nobel Prize. So the more will come from Professor Kajita. But this also make me stepping into the international arena to become the president of aeronautical meteorology in the World Meteorological Organization. Standing there next to me was my vice president from the United Kingdom. I'm still the president, but I will be finishing my term this July. Anyway, I suggest to you that if you have a passion and inspire in science, you can do something good for the society. I think that is another reason why you need to develop your passion and interest. Of course, uncertainty is good or bad, but if you don't have uncertainty, I think you have no room for more discoveries. You never be sure. Today, the law of physics could be challenged by something new, and that is discovery. But I am actually facing this on a daily basis. Every day, you know that weather forecasts cannot be 100% correct. So we have to explain to the public why we failed on a forecast. So for example, if the typhoon last year, the Hato, took on a different track, slightly closer to Hong Kong, then we will be in big trouble. I think most of you haven't been born yet in 1962, when there was a Typhoon Wanda, which hit Hong Kong directly and then killing more than 100 people. If this typhoon took a similar track, then we will be in deep trouble, and I may not be standing here to talk to you today, because the director will have been fired, like the director in Macau. Now, another question that I think we all need to face is artificial intelligence. Why I want to talk about this is that people seem to be now really impressed by the performance of the computer, by AI, by AlphaGo, that it may replace the human in a lot of things, like Aaron has mentioned, to take on a career on medicine or law or even finance. Do you know nowadays financial analysis can be done by AI? There are legal services by the computer, by robots. So in the future, we have to think really hard how to choose our career in order not to become obsolete due to the AI, robots, and artificial intelligence. And there is also, I think, a developing illusion that because of how the strength of the computer, so that the forecast, the weather forecast, or even any other predictions should be faultless. No error accepted. I think this is wrong. But we have to try harder to explain to people why there are uncertainties. And in fact, we should live with uncertainties. And I'd like to show you this again. I think it's not a joke. Why Donald Trump, he doesn't believe in climate change? Maybe it's because of scientists not able to deliver the message why forecasts, why climate predictions could not be 100% correct. Why is it's still freezing cold in the winter while we are talking about global warming? So I think what we are doing in science is really significant for the society. And I'd like to end my presentation with the values of the observatory that we build on the 7 characters of science, and we want to impress all of you that science is a career that we should choose in order to excel in the future. This is a newspaper cutting that I was interviewed. Sorry, it's Chinese, but it says that science is just a subject that nowadays nobody like to enter into. But I don't agree. Actually, we should try to inspire people, especially that we can learn many things new, and we need to help people, and including ourselves, to appreciate uncertainty and live with uncertainty, and also the meaning of doing science as a career. It's not about making money, it's about saving lives, it's about the betterment of society. Thank you very much.
Thank you, Mr. Sun. Another big round of applause to Mr. Sun. So you got a very tough job. It's not an easy job. Now, we have reached the climax of tonight's event. So we will have Professor Takaaki Kajita, a Nobel Prize winner in physics in 2005. And he will be sharing with us how will the development of neutrino oscillation affect our future. So ladies and gentlemen, a big round of applause to the professor.
Oh, it's okay, it's okay. Okay. Good evening. Well, it is my honor and pleasure to speak here. So, this evening, I would like to discuss the discovery of neutrino oscillations. Well, first of all, you see some photo here. And this is the detector we have been working. And this is Super Kamiokande. And with this device, we observed that neutrinos have mass. Neutrinos oscillate. OK, so the outline of this talk is here. First of all, I want to have an introduction of myself a little bit. Then I want to talk about neutrinos. It's also a very, say, simple introduction of neutrinos. But, well, if you have no idea about the neutrinos, then the whole talk may have no meaning to you. So I want to have some discussion about neutrinos first. Then, well, I want to talk about my studies from the early days, that was about 35 years ago, discovery of neutrino oscillations and the importance of neutrino mass and summary. OK, well, introduction of myself. Well, actually, well, I want to begin with the undergraduate age, where I enrolled in Saitama University. That was a local national university near Tokyo. Although I thought I should learn physics as a physics student, but I was more involved in Japanese archery club in the university. I thought that some lectures in physics were inspiring. However, I did not spend much time in learning physics until the end of the third year. By the way, this is a photo of myself playing Japanese archery. Well, anyway, at the end of the third year, I had to think about my future. So before the end of my third year, I decided to go to graduate course and to study physics seriously. Actually, it was not an easy decision, because in the Japanese archery club of the Saitama University, the person who played the role of sub-captain in the third year should become a captain in the fourth year and most seriously play Japanese archery. That was a kind of tradition. So I decided to decline from being a captain. And after many discussions with my colleagues, people finally agreed with me. So I began seriously studying physics at that time. And very fortunately, Professor Koshiba of the University of Tokyo accepted me as a graduate course student in his group in the Department of Physics. OK, so this is my early history. And after enrolled in the graduate course, I began studies of physics rather seriously. And the studies were all related to neutrinos. Therefore, I want to talk about the neutrinos a little bit. Now, actually, neutrinos are small particles. And I'd like to introduce the small world. Well, you know, all of us are made of atoms. And they are very small particles whose size is around 10 to minus 8 to 10 to minus 7 centimeters. But people asked, are there any structure inside? And the answer is yes. Well, at the center of the atom, there's a nucleus whose size is very small, around 2 times 10 to minus 13 to 10 to minus 12 centimeters. And around this nucleus, the electrons are surrounding. Then people still asked, what is the substructure of this nucleus. And we know that nucleus is made of many protons and neutrons. And people still asked, are there any inner structure in the protons and neutrons? The answer is yes. For example, a proton, in the proton, there are, no, it's too simplified. Okay, if I simplify the structure of proton to the extreme limit, then the proton is made of 2 up quarks and 1 bottom quark. And the neutron is made of 2 down quarks and 1 up quark. So we know that these particles are made of quarks. And you may ask, what is the inner structure of quarks? Well, we know that, well, so far, we do not know if there is any substructure for quarks. So in this sense, quarks are the most fundamental particles. And electrons are also fundamental particles. We have no idea if there is any inner structure. So electrons and quarks are the most fundamental particles. But you notice, so far, there's no neutrino. Well, in fact, neutrinos are also fundamental particles, like electrons and quarks. And neutrinos are, well, something like electrons without electric charge. In fact, this has a very significant consequence. Well, electrons were surrounding the nucleus, and because, well, nucleus has plus charge and electrons have minus charge, therefore they attract each other. Therefore, they form an atom. But neutrinos have no electric charge. Therefore, even if a neutrino comes close to a nucleus, neutrinos doesn't feel the electric field. So neutrinos just pass through the nucleus. And this has a significant consequence. As I write down here, neutrinos can easily pass through even the Earth. But they can interact with matter very rarely. And therefore, it is possible for us to study neutrinos. OK, well, I have actually 2 more pages on neutrinos. Well, this is, OK, simple introduction, one more introduction. Neutrinos have, like the other particles, 3 types: electron neutrinos, muon neutrinos, and tau neutrinos. Well, I'm sorry for this, but anyway. And finally, I want to say that neutrinos have been assumed to have no mass. OK. So you almost understood neutrinos. Well, then maybe you ask, if the neutrinos are like this, how can we study neutrinos? Well, of course, we have no way to observe neutrino itself. But we have a way to observe neutrinos because neutrinos very rarely interact with the nucleus. Then a charged particle is emitted. And if a charged particle, for example, an electron, is emitted, then we have various ways to observe these particles. For example, in our experiment, well, we use water. And if a charged particle or an electron propagate in the water, then photons are emitted. And of course, we have various ways to observe photons. We have various photodetectors. Therefore, we observe these photons. And therefore, we know that charged particles propagate in the water. And through this information, we knew that a neutrino interacted there. OK, so that is the way we observe neutrinos. Now, from now on, I want to discuss what we studied. Actually, the whole story of our research began about 40 years ago. In the 70s, new theories of elementary particles predicted that protons should decay with the lifetime of about 10 to 30 years. OK, so I guess you have no interest in the life of proton. 10 to 30 years is a very long lifetime. Even if protons decay or do not decay, our life doesn't change at all. However, the finite proton lifetime has a very important consequence, scientific consequence. Therefore, several proton decay experiments began in the early 80s in the world, and one of them was the Kamiokande experiment. And this is the sketch of the Kamiokande detector. It is a big water tank. It had about 16 meters in diameter and 16 meters in height. And well, inside, there were a lot of photodetectors. And these photodetectors observed photons that were generated or produced by charged particles propagating in the water tank. And it contained about 3,000 tons of pure water. By the way, you have no idea where is this detector, where was. Well, OK, the detector was located there. So you notice that the detector was in the mountain area, and you are right. The area looked like this. Well, actually, this photo was much recent one, taken in March '96. But anyway, this is the area where the Kamiokande experiment was located. Well, in fact, the experiment was located inside the mountain in the left. It was located 1,000 meters from the top of the mountain, so it was located in a very deep place. And well, actually, as a cosmic ray scientist, we had to construct our detector in underground. So we indeed constructed the detector. And this photo was taken in the morning in the spring of 1983. At that time, we constructed the Kamiokande detector, and this photo was taken when our boss, Professor Koshiba, came to the site. By the way, you notice that, well, we had the helmet, rubber boots, and the working clothes, and the flashlight. So this was the way we worked in underground. And in fact, well, after taking this photo, we took a train, well, mine train, together with the mine workers, and went into the mine. Oh, by the way, well, behind Professor Koshiba, there are 4 young students, and one of them was me. And, well, we worked in underground every day for several months to construct the Kamiokande detector. the actual work was like this. As I said, well, the Kamiokande tank was about 60 meters high, and we had to install the photodetectors onto the detector wall. So there was a big discussion. How shall we install the detectors, photodetectors onto the wall? Initially, we thought we make some kind of structure inside the tank. But, well, that kind of temporary structure is typically very scary. Therefore, after some discussion, we decided to use these rubber boards to install the photodetectors. Well, on a day, we work at the level, and if we finish the installation of the whole row, then we raise the water level and put another photodetectors onto the upper level. So, like this, we worked on the boat for maybe 2-3 months. But, well, I think we were lucky. No one dropped to the water. Anyway, well, actually, I enjoyed these works very much. Well, some people think that these kind of work are not for scientists, but, well, I enjoyed these works. And also, I was excited because I thought that the data from Kamiokande may contribute to physics much. So around that time, I decided to be a physicist. Anyway, the construction of the Kamiokande finished in early July 1983, and we began the experiment. Unfortunately, well, we thought that we would observe proton decays rather frequently. Maybe, well, if we were lucky, we should have observed proton decays, say, in every few days. But soon after starting the experiment, we realized that there's no evidence for proton decays. Instead, the most serious noises for the proton decay searches have been observed. These are the neutrino interactions. Well, maybe you ask how these neutrinos are created. In fact, these neutrinos are created by cosmic ray interactions in the atmosphere. Oh, by the way, you do not know what are cosmic rays. Well, cosmic rays are particles, high-energy particles coming from somewhere to the Earth. And they are high-energy, say, protons, or high-energy helium nucleus, sometimes high-energy, even an iron nucleus. They come to the Earth. So these cosmic ray particles interact with the air nucleus and produce some pions, which are elementary particles. But these pions are unstable, therefore they decay to some other particles. And during this decay chain, neutrinos are produced. And these neutrinos are observed in underground Kamiokande. So these are the most serious background or noises for the searches for proton decays. And therefore, at some point, we had to improve our analysis software in order to better separate the proton decay signal and the neutrino noises. So after 3 years, in 1983, we developed new software to improve the proton decay analysis. Well, we did various things, but, well, one of them tried to identify the neutrino type or particle type, and this is a typical event observed in Kamiokande. We'd like to know this was due to an electron neutrino or a muon neutrino. So we developed a new software. But of course, if we developed a new software, we have to test this software extensively. If you write some software, typically this software contains a lot of bugs, so this software doesn't work at all. Even if after some debugging, software seems to work properly, but usually there are still some problems. So we have to extensively check the software, and in fact, we did. And as a test, as a final test, the neutrino type was studied for the neutrino events so far observed in Kamiokande. Then it was found that the number of muon neutrino events was much fewer than expected. And this means, since we are testing the new software, the software must contain some bug. So there must be some problem. So we began the work to find out mistakes somewhere in the software. That was the end of 1986. And well, actually, we worked for about a year. But we didn't find any mistake. So, well, since we worked hard for a year, we concluded that maybe the muon neutrino deficit cannot be due to any major problem in the data analysis or no other simulation. So we decided to publish our data. And this is the essence of our publication paper. Well, usually people have a feeling that scientific papers are difficult. But in this case, it was easy. Well, we simply reported the number of muon neutrino events observed. That was 85. We also calculated the expected number of muon neutrino interactions. That was about 144. So the number of observed muon neutrino events was much fewer than expected. Also, we did the same thing for electron neutrino events. For the electron neutrino events, the observed data and the expectation agreed reasonably well. So that's all what we reported. Well, although we had no clear idea what was the cause of the deficit, but I was most excited with the data. In fact, as a scientist, I enjoyed to find out the cause of the deficit, and therefore, in my opinion, around that time was the best moment for me as a scientist. Anyway, since to me, this data may contain very important information, so I decided to change my research from the proton decay searches to neutrino studies. Oh, by the way, I said we had no clear idea what was the cause of the deficit. But, well, in fact, from the beginning of the studies, we had been thinking that maybe, this is still maybe, but maybe neutrino oscillations could be the cause of the deficit. Well, I have no explanation so far about the neutrino oscillations, but let me explain. If neutrinos have mass, neutrinos change their flavor, type, from one type to the other. For example, a muon neutrino created at the left end propagate to the right, then they change the type to tau neutrinos. But if they propagate further, then it becomes muon neutrino again. Propagate further, become tau neutrino. This way, neutrino type changes. This is called neutrino oscillations. And in fact, this phenomenon was predicted more than 50 years ago by theorists, several theorists. So we thought that neutrino oscillations might be the solution to the atomic neutrino deficit. However, we have another possibilities. Therefore, we needed to find out the real cause of the deficit. Oh, only 5 minutes left. No. Okay, well, anyway, so let me continue. So, well, so we needed to separate the neutrino oscillation from other possibilities. So we thought this way, maybe, well, neutrinos are produced by cosmic ray interactions everywhere in the atmosphere. Therefore, some of them are produced in our upper atmosphere. And these neutrinos come to the detector soon after the production. Therefore, they may have no time to oscillate. But neutrinos are also produced in the other side of the Earth. Therefore, they need to travel long distances. Therefore, they may have long time to oscillate. So this way we thought, and we thought that we should observe up versus down asymmetry of the atomic neutrinos. And if we observe this, this should be the evidence for neutrino oscillations. However, well, 3,000-ton Kamiokande detector was too small for this study, and we needed the super Kamiokande detector. Well, okay, since the time is quite limited, I cannot go into details of the super Kamiokande experiment, but it is a much larger version of the Kamiokande detector, about 20 times larger, and it's an international collaboration. And this is a photo of us constructing the super Kamiokande detector. So many people worked in underground for about a year to construct the super Kamiokande detector. And well, this is a photo of the water filling. And after that, we began the experiment in April '96. And well, actually, the detector worked quite well from the beginning. And this is the, one of the events observed in super Kamiokande. So we observe these neutrino events every day, about 10 neutrino events every day. And we analyze these events as a team. And in fact, in 2 years, we were able to announce our first result. Well, okay, that the slide copied in the right is the one we used at the conference, but well, let me explain the essence. That is the lower part, well, copied here. So here, we plotted the number of muon neutrino events as a function of the neutrino direction. 1 means downgoing, -1 means upgoing, coming from the other side of the Earth. So clearly, for neutrinos coming from the other side of the Earth, the observed events shown by crosses are about half of the expectation shown by boxes. So this is clearly indicating that neutrinos traveling long distances oscillate. So this way, people were convinced that neutrinos oscillate. Now, soon after our presentation, President Clinton President Clinton of the United States made a remark at MIT. He made a speech. And, well, the whole speech is about 1 hour long. Therefore, I made a copy of the relevant part to our experiment, and which is shown here. And I want to read. Just yesterday, in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories, from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. So, by the way, this remark was made on the next day of our conference announcement. Anyway, he continued, and I want to read. The larger the issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. So, well, I think it was really an honor for us to hear this kind of remark by the US president. And of course, well, I don't know if the discovery were 20 years later, this year. Anyway. Now, well, it was really great to hear the remark by the US president, but, well, maybe you do not know why the US president needs to mention our result. Why so important, the neutrino mass? Now, let me convince you that neutrino masses are, in fact, very important. Well, this plot shows the masses of charged leptons and quarks. So there are 3 charged leptons and 6 quarks, and these masses are shown here. And, well, we know that neutrinos have mass, and the discovery was made 20 years ago. And after that, there were a lot of studies on neutrino mass. And therefore, at present, we can plot a neutrino mass, although we still have some assumptions. But anyway, let me plot the neutrino mass here. And they are here. First of all, you notice that neutrino masses are located in a very different place on this plot. But be careful. Well, about the horizontal axis. Here, the 1 unit is 2 orders of magnitude. So if there is 2 unit separation, that means 10,000 different. And then if you count how much separation in the mass, then you notice immediately that neutrino masses are approximately, or maybe even more than 10 billion, that is 10 orders of magnitude. smaller than the corresponding masses of quarks and charged leptons. More than 10 orders of magnitude difference. That is significant. And we believe this is the key to better understand elementary particles and the universe. Of course, it's very important to understand this smallness, extreme smallness of the neutrino mass to understand elementary particles. But why universe? Well, let me explain what we are thinking. Well, here I simply show you a copy of the far universe, picture of the far universe. And well, there are a lot of galaxies. And we know that these galaxies are made of matter particles. We know that there's no antimatter galaxies. Oh, by the way, of course, some of you have no idea what are antimatters. Well, if there is a matter particles, there is always antimatter particles. For example, a proton which has +1 charge exists. Then there is antiproton which has -1 charge. So always there is matter particles and the antimatter particles. Now, so all these universe galaxies are made of matter particles. But this is strange, actually. We know that the universe began with Big Bang. And well, in the Big Bang universe, the universe was extremely hot. And in this extremely hot universe, particles and the antiparticles were always created simultaneously. And also, if particles and antiparticles meet each other, then they disappear. So in the Big Bang universe, there must be equal number of particles and antiparticles. But now, in the present day cold universe, we only see matter particles. Why? Well, we somehow understand this problem. At the Big Bang universe, there was about 1 billion matter particles and 1 billion antimatter particles. They were almost equal. And after the Big Bang, the universe cooled down, and if the matter particles and the antimatter particles meet, and they annihilate. So at present, we have this 1 matter particles. This is the scenario we are thinking. But, well, this is kind of cheating. We should have equal number of matter particles and antimatter particles at the Big Bang universe. But, well, 1 billion is not equal to 1 billion. So we need to explain why there was extra one in the matter particles. And we think that neutrinos with very small masses might be the key to understand the big mystery of the matter in the universe. That way, neutrinos with small mass are relevant for us to understand the big mystery of the universe. Okay, let me summarize. Well, I talked about our discovery of neutrino oscillations, and atmospheric neutrino deficit was observed unexpectedly in proton decay experiments. And subsequently, in 1998, Super Kamiokande discovered neutrino oscillations, which shows that neutrinos have mass. The discovery of non-zero neutrino mass opened a window to study physics beyond the standard model of particles. Neutrinos with small mass might also be the key to understand the fundamental questions of the universe. So we think we still have to study more on neutrinos. And well, finally, I want to talk about myself. I feel that I was very fortunate. I had very good advisors, colleagues, and I was always involved in very good projects. So if you want to do something, for example, science, my message is, please do not hesitate to do so. Yes, you can. Thank you very much.
Thank you, Professor Kajita.